Okay, good afternoon. We'll continue today with a new topic. Today we will talk about the gravitational potential energy and the conservation of energy between gravitational and kinetic energy. In the next lecture, we will be talking about conservation of energy, including the loss. So today we will be talking or using a lossless system and also the power. So before we start talking about the conservation of energy, I would like to solve a few examples about the work energy theorem. So in this example, we have a girl pulls a wagon load of toys with mass 20.8 kilograms across the horizontal ground. She's exerting a force on the wagon of 95.6 Newton, inclined at 35 degrees above the horizontal. The kinetic friction force on the wagon has a magnitude of 75.5 Newton. We need to use the work energy theorem to determine the speed of the wagon after being moved 0.75 meter, assuming it starts from rest. So starting from rest means that the speed is 0 at that moment. Okay, so where shall we start from? Again, the free body diagram. We need to draw the free body diagram for this problem we have here. Before I draw it, I have the mass 20.8 kilograms. I have the tension force 95.6 Newton. I have the theta of the inclined plane above the horizontal, 35 degrees. I have the kinetic friction energy, Fk, as 75.5 Newton. Use the work energy theorem to determine the speed of the wagon. So we are looking at the wagon speed at the final destination. If we know that the displacement, the magnitude of the displacement is 0.75 meter. And starting from rest, which means V naught is 0. So that's the wagon. This is the tension force. This is the horizontal, 35 degrees. Or I can put theta here. Kinetic frictional force. Gravitational force. Normal force. I would like to put my coordinates such that x is pointing in the direction of the motion here. We have y. Now what's going to happen, starting from rest, which means at this point, I have V naught equals to 0. So this is going to go a displacement of delta R. So the wagon is going to be here. And speed is unknown. I need to use the work energy theorem to calculate the speed of the wagon after the wagon moves a displacement of 0.75 meter. So what's the work energy theorem? Work energy theorem says that the exerted work equals to the change in the kinetic energy, such that it is the final kinetic energy minus the initial. So this moment is the initial, and this one is the final. The initial has a speed of 0, which means that the kinetic energy at the initial is 0. Why? Because I know the kinetic energy is half mv squared. If the speed is 0, then the kinetic energy is 0. So let me start by calculating the work. What does the work say here? The work in general is the force, magnitude of the force, times the magnitude of the displacement, times cosine the angle in between. I'm calling it phi here, just to distinguish between this angle and the theta that I have in my drawing. Phi is the angle between the force and the displacement. So in this problem, as you can see, I have two forces that are contributing in the motion of this wagon. The tension and the kinetic frictional force. The force that is responsible for the work, if you recall, is the force along the displacement motion. Is that right? So in this case, if I am to project this tension force that has an angle of 35 degrees with the horizontal, get its components on X and Y, I can tell the force, which force is responsible for the motion. So what I'm going to do, I will define those components. So I have here Ty and Tx. Now, looking at the Tx, Ty, Fn, Fg, Fk, I can easily see that the forces that are responsible for the motion are the Tx and the Fk, right? And the motion is happening in the direction of the tension force, which means that the net force along the X component is indeed, do you know, F net along the X is what? Tx minus Fk. Tx minus Fk. This is the force that's causing the acceleration. That's the force that is exerted on the wagon that is resulting into the induced work. What's the angle between this force and my displacement? Zero. This F net X is on the X-axis. And the displacement, the motion is happening on the X-axis. So the angle between this force and the displacement is 0. So here, first of all, I need to find, so this is T cosine 35. minus Fk F net x is 95.6 times cosine 35 degrees minus 75.5. Then F net x is is 2.81 Newton. So if I go back here, I'll try to draw this. This is F net x. So I found the force that is responsible for the work. Now I go here. W equals 2 F net x times delta R times cosine 0 degrees 2.81 times 0.750 times 1. And the work is 2.11 joules. This is the work done by that net force. So in case I don't have a friction, then the only force would be responsible for the work is, if I don't have a friction, if I don't have this kinetic frictional force, then the force responsible for the work is Tx. Or you can take the general expression, which is T cosine 35 times delta R. At the end, they're the same. If you say Tx is T times cosine 35. But now, since we have a frictional force, then we have to include the frictional force in the total force responsible for the work. And that's why we took the net force along the x-axis. We picked the x-axis because this is the direction of the motion, right? And in this case, the angle between the force and the displacement would be 0 because they're on the same axis. So we found the work. Now back to the work energy theorem. We know that W equals to EK final because the EK initial was 0, right? And now this W equals to half m v squared, where v is the final speed. Or rearranging, v is square root of 2 times W divided by m. V is 2 times 2.11 divided by 20.8. Then V is 0.450 meter per second. So we use the work energy theorem to calculate the speed. If you recall, we can use the kinematics equation also to find the speed. So this is, you can look at this approach as a second approach. So you can find the speed with the kinematics, or you can find the speed with the work energy theorem. In the kinematics, you would be finding first the acceleration using Newton's second law, and then from the acceleration you can find the speed at the final destination. You know the displacement, right? Okay, so let's move on. Now let's look at this example where we need to calculate the work done by the gravity. In this example, the question is the following: what is the work done by gravity if a 110-gram apple falls from 5 meters above the ground? Assume the apple starts from rest. What is the final speed of the apple just as it hits the ground? This is another example that we could use kinematics to find the speed. But this time we want to use the work energy theorem. We need the final speed. Okay, so we have an apple. (110 grams), which means m is 0.11 kilograms. Above the ground, I'll take the ground as my reference. We need the final speed, so we have the initial speed as 0. We need the final speed. So if that's the apple, and this is the ground, this is x, and this is y. If I take this as y naught equals to 0, and this one is y equals to 5 meters, then I have the gravitational force pointing this way. Right? And in this case, I also have the displacement. So that apple is going to fall, and this is where the position right before it hits the ground. So in this case, I can say that the displacement is this. This is delta R. Is that right? This is the displacement. And the gravitational force is pointing in the same direction as the displacement. It is extremely important to start the first thing to do is to draw the free body diagram. Don't jump into conclusions when it comes to solving such problems, because the free body diagram will make things clearer to you when it comes to the angles, when it comes to the vectors, things will be very clear. So if I want to calculate the work, I know now that based on the work energy theorem, I know W equals to delta E K. I'm starting from the rest here, which means V naught is 0. I don't know V. I need V. So work equals to EKF minus EK initial. So this is the initial. This is the final. Since it's starting from rest, kinetic energy is 0, which means that the initial kinetic energy is 0. So I ended up with W equals to EKF. So what is W? The force, Fg, times the displacement, magnitude, times the angle. How much is the angle between the displacement and the gravitational force? 0. So cosine 0. So W is the mass times the acceleration of the gravity times 5 times 1, and the work is 5.4 joules. This equals to EKF. W equals to half mv squared, and this v is the final. Again, v is square root of 2 times w divided by m, or v is 2 times 5.4 divided by 0.11, and then the velocity is 9.9, or the speed is 9.9 meter per second. Try calculating the speed using the kinematics. Which equation you will be picking? I have v squared equals to v, let me call this for y naught squared, plus 2 ay, y minus y naught. Based on the directions of the positive coordinate along the y, positive y is up. I have the acceleration pointing down, and we said that in this case, we will substitute the acceleration as minus 9.8 in this equation. And the displacement is also pointing down, which means the displacement would be also minus 5 in this case. And this is 0 because we're starting from rest. So we have Vy squared equals to 2 minus 9.8 minus 5. If you do the calculation, you will see that Vy is 9.9 meter per second. Either way, you should be getting the correct answer. Remember, we're dealing with the lossless system here. We have 0 air resistance. Any question about how did we apply the energy work theorem to find the final speed? No questions? Everything's clear? The gravitational potential energy. The gravitational potential energy is an energy that is related to the position of the object with respect to the ground. So if we take the ground as our 0 reference potential energy, then if you raise the position, raise the object at any position, the acquired gravitational potential energy for that object is related to the distance of this object to your reference. So in other words, if this is the calculator, if it's the gravitational potential energy of this calculator on the ground is 0, raising it up this height, the calculator acquired a potential energy based on its location to that reference point that you have defined. So right now, this calculator has gravitational potential energy, zero kinetic energy, right? Because it's a stationary. But if I let go, it will fall down, decreasing its potential energy, increasing its kinetic energy. So the gravitational potential energy is a function of the distance, of the position with respect to your reference. If you take the ground here as your zero potential energy, then the potential energy for this calculator is based on the height of this calculator with respect to your ground. So the expression that defines the amount of the gravitational potential energy has, first of all, you have to have a reference that you assume to be your zero gravitational potential energy. So in this case, the EP, which is the gravitational potential energy, is given as the mass times the gravitational acceleration times the distance to your reference. The unit is joules, Newton meter, right? Joules. And this quantity is a scalar quantity. We'll see an example. Here in this example, we have a 200-gram apple that has a 4 joules of gravitational potential energy due to its height from the ground. So assuming that the ground is your reference, your zero. How high above the ground is the apple? Can you find out how much is the height? What do you do to calculate the height of that apple that has a mass of 200 grams and the gravitational potential energy of 4 joules? Look at the expression that we have just introduced. EP equals to, assume that G is 10 for simplicity, mgy. So we need y. Y is EP divided by mg. EP is 4, mg is 2. So 4 divided by 2, then the answer is 2 meters. Let's have a look. Let's watch this movie. In this movie, we have, as you can see, someone throwing the ball up straight, giving it an initial velocity right at that reference point. So if we assume that this reference point has a zero gravitational potential energy, then this ball has only kinetic energy, right? This ball is going to go up till it reaches its maximum height. What's the speed right there at this maximum height? The speed right at the maximum height is 0. So the kinetic energy right up there is 0. So at that point, I only have potential energy, which is a function of the height from the reference level, right? However, when I threw the ball, I only gave it kinetic energy, has 0 gravitational potential energy. But what happened is that ball was going up, slowing in velocity, in speed, till it reaches a point where it has 0 kinetic energy, only potential energy. And then flips and goes down. Now the gravitational potential energy starts to decrease, the kinetic energy starts to increase. So it's going this way. One of them goes up, the other one decreases, and vice versa. However, at any point along this path, the summation of the potential and the kinetic is constant in lossless systems. And that's what we call the conservation of energy. The energy is conserved. Again, lossless system. The energy is conserved, which means the energy is not going to be destroyed or created. It transforms from one shape to another. And that's why it transforms from potential energy to kinetic energy and vice versa. Or from kinetic energy to gravitational potential energy. And the maximum gravitational potential energy it reaches is the highest point it can reach. Is this understood? Yes? We will see an example. Here you throw a ball mass of 2 kilograms directly upwards with an initial speed of 2 meters per second. The ball rises to a maximum height of 0.204 meter before falling back down again. Set the lowest point as your reference point for the gravitational potential energy. And I will show you now how the energy is conserved. So if this is my reference level, where I'm calling y naught equals to 0, where I have the gravitational potential energy here being 0, and this is the maximum height. So the ball has the gravitational force pointing down this way. If I put my coordinates, x, y. Now I know that the velocity here or the speed here is 0. And I know that the speed here, so let me call this one at point A, and here point B. So I don't know VB, but what I know that VA is 0. So if I am to calculate the gravitational potential energy at point A and the kinetic energy at point P and point A as well, then I have EPA equals to mGYA. EPA as, what's the mass? 2 kilograms times 9.8 times, what's the height? 0.204. EPA is 4 joules. What is EKA? What is the kinetic energy at point A? 0. Why? Because the speed at point A is 0. Then EKA is 0. Since VA is 0. Now, if I take EPA plus EKA, the results would be 4 joules. So this is at point A. At point B, I have EPB is 0. Why 0? Because this is my reference. That's my reference. Y is 0 at that point. EKB as half m. I know BB here. It's 2 meters per second, right? BB is given to me 2 meters per second. Half m BB squared EKB half times 2 times 2 squared EKB is 4 joules. So EPB plus EKB equals to 4 joules. So you can see that the energy is conserved at any point along this path. In this system, energy is conserved. If you try to calculate the speed right in the middle using kinematics equation and calculate potential energy and the kinetic energy, add them, the answer should be 4 joules. So any point along this path, the energy is conserved, the summation of the gravitational potential energy and the kinetic energy should be 4 joules. Is that clear? Any questions so far? Okay, so let's look at this example here. Here, if we have a girl that has a mass of 50 kilograms, and we assume that the acceleration is 10 meters per second squared for simplicity, then right at point A, if you calculate the gravitational potential energy, you will find out that the energy is 50 kilojoules. Since the girl is standing there, she's at rest, her kinetic energy is 0 joules. Now, based on the conservation of energy, at any point in that path till she reaches the ground, the conservation, based on the conservation of energy, the total amount of energy should be 50 kilojoules anywhere. So look at point B. The summation of those two energies is 50 kilojoules. Point C, 50 kilojoules. Point D, point E, anywhere the energy is conserved in this lossless system. We have 0 friction here. Now let's look at this example, try to implement the conservation of energy approach that we talked about to solve for the speed at this point. So the question reads the following: a diver starts from rest at 13.6. The word from rest means speed is 0. Also means kinetic energy is 0. So just keep this in mind. When you hear the word rest, this means the speed is 0, kinetic energy is also 0. So he's starting from 13.6. What is the diver's speed when he is 3.4 meters above the surface of the water? Solve this question using the principle of conservation of energy. So my reference For zero, gravitational potential energy is the level of the water. So this is my reference level. This is Y naught, 0 meter. I have here the 3.4 meter and the 13.6 meter. Now, V naught here is 0. I only have the gravitational force. I need the speed right here. So if I put my coordinates now, such that this is my X, and this is my Y. And I calculate the gravitational potential energy and the kinetic energy at those 2 points. Now, based on the conservation of energy, the summation of the potential and kinetic at 13.6 should equal the potential and kinetic at 3.4 meter. And this is what I'm going to do. So at the beginning here, I will calculate EP naught here, which is mgy. I don't know the mass of that diver. I only know the height and I know the acceleration. So AP naught m times 9.8 times 13.6 EP naught as 133.3 m, and this is joules. So it's a function of the mass. What about the kinetic energy right up there? 0, right? Because the speed is 0, so this is 0. The next point, so here is at 13.6 meter, here at 3.4 meter, I have EP F equals to mgy. EPF, I don't know M, I know G, I know Y. And in this case, EPF is 33.3 M. It's a function of the mass as well. What about the kinetic energy? EKF half M V squared. I don't know the mass and I don't know the V. I'm solving for V. But now what I'm going to do, I'm going to apply the conservation of energy. Applying the conservation of energy, I have E P naught plus E K naught equals to EPF plus EKF. Ek naught is 0. I know that because the kinetic energy there is 0. EP naught is 133.3 m equals to EPF is 33.3 m and EKF is half m v squared. Is that right? This is from applying the conservation of energy. Since m here do exist and everywhere, I can divide by m and get rid of the m. So dividing by m is gone. So I end up with 133.3 equals to 33.3 plus half v squared, or v is square root of 2 times right? And v is 14.1 meter per second. Any question? How did we calculate the speed? Now let's look at this example. Here, in this example, we have two apples that have the same mass. One of them is at a height of 1 meter, and the second one is at a height of 9 meters. What is the speed of apple B that is at the height of 9 meters in comparison with the speed of apple that at 1 meter when both of them reach the ground, just before they hit the ground? Are you expecting the apple that is at a higher height to have a speed before it hits the ground that is greater than the apple that has a lower height? Yeah, yes. But do you know the number? Do you know how much is the ratio? Okay, so let me do this. So we have apple A and apple B. So apple B is at a height of 9 meters. Apple A is at the height of 1 meter. So this is 1, this is 9. So if I put my coordinates here, and I find the I find the kinetic energy and the gravitational potential energy for both of them. So let me start first with apple A. For apple A, starting from rest, both of them, then the kinetic energy at the initial, so this is initial, here and here, and this is final. This is final, right? So for apple A, EP initial as mgy. So this is for A. Let me keep A here. So EP initial for A as mg times 1. Ek initial for A is 0, right? Fine. Now, EP final for A is 0 because right at the level of the ground, the gravitation potential energy is 0. This is my reference. Ek F A is how much? Half mVA squared. Right? Now, applying the conservation of energy, what do I get? I get here EPIA equals to EKFA, right? Which means mg, the one is gone, equals to half mVA squared. Is that right? Now, if I do the same for B, the only difference is the y, right? So the same, doing the same. For B, I get mg9 equals to half VB squared. Is that right? Now, divide those two equations. What do you get? You get mg over mg9 equals to half mVA squared over half mVB squared. mg is going to cancel, half m is going to cancel, so you end up with VB squared equals to 9 VA squared. Right? Or VB is 3 VA. So it is the square root of the height difference. So apple B is 9 times higher than apple A. The speed is the square root of this difference, the square root of this ratio. And that's why the speed of apple B before it hits the ground is 3 times the speed of apple A. Now, before I stop, I just want to tell you to try solving this example on your own. There's no difference than what we have done. You have, this is point A. You can calculate the kinetic energy here. And also from the height, you can calculate the gravitational potential energy. For point B, the gravitational potential energy is 0. You only have the kinetic energy. You can calculate the speed before it hits the ground using the conservation of energy. Gravitational kinetic at A equals to kinetic at B. Okay? Thank you so much. I'll see you on Monday.